Mr. Tarot, in this video we are going to introduce the idea of differentials and look at quite a few examples dealing with tangent line approximations and estimating propagated errors. Most of our examples are going to deal with the errors. Now, a lot of the functions we deal with in calculus are quite complicated, whereas a tangent line is a linear function. And we've been working with linear functions since really kind of like pre-algebra, right? So some mathematics are easier with or in linear calculations as opposed to some of these complex functions we deal with calculus. Thus, this idea of differentials is going to teach us how to approximate the values along, these functions we have in calculus, these nonlinear functions, and we're going to estimate a change in a function over a given horizontal distance of x with this tangent line. But as you can see from my drawing, if your function is curving all over the place and a tangent line is linear, the estimation that tangent line is going to give you is only going to be somewhat accurate as you are close to your tangent point. So we can't always use tangent lines to estimate values or changes in values of a function. It has to be, pretty close to that point of tangency. Excuse me. But like manufacturing processes. When companies try and manufacture, say, a ball bearing, they're not all going to be exactly the same, right? But they're going to vary a little bit. So there's a lot of applications in the real-world setting where a parameter is set, but there are small variations from that value, just say, through a manufacturing process. So it's very reasonable to think that we will have situations of having small changes in some parameter and then looking for some kind of response. Maybe the change in the radius of a ball bearing, a spherical ball bearing, is going to change how much volume or mass that has. So that little bit of change in the radius, we're going to talk about how that error in the radius, as an example maybe, would create a propagated error in the volume of that sphere. Okay. Some of these calculations are going to be pretty straightforward, and some of them are going to, be quite a bit more difficult. So I'm going to try in this first scene let you understand or help you understand what all the symbols mean. So we have a function here, and we have a point of tangency, CF of C. We've moved over a certain value of x, in this case to the right, and thus we have an x-coordinate of C plus delta x, which we know is just a change in x. And from that, of course, we get a new value on the function, and that value is going to be c plus delta x, comma, f of c plus delta x. Now, like I said, it may be a situation where finding that amount of change in y, the actual change in y, is quite complicated. So what we'll do is we'll find a tangent line at that point of tangency cf of c, and then we would be able to a bit more easily calculate the amount of change that we have in the tangent line and then use that to approximate the change in the actual function. So the change in the tangent line is going to estimate the amount of change in the actual function. And of course, as we get closer and closer and closer to that point C, we can see that the vertical differences, because we're estimating y values basically in this particular example, are going to get closer and closer to 0. I mean, become infinitely accurate the closer we get to C. So we have this idea of CF of C, or point of tangency. I've highlighted just another random point, so it's not a completely random point, on my tangent line of actually using the same x-coordinate for these 2 points, which we can see is C plus delta x. I'll explain in a little bit why I have just xy in this tangent line. And that vertical distance is going to be labeled as the y of, some points or on the tangent line minus f of c, the initial point or the point of tangency between the tangent line, of course, and the function. We'll see how that is changed to c prime or f prime of c, or the first derivative of f at c, which we know is slope, delta x, and that as a math symbol is going to be labeled as dy. And as I move out of the way, we'll eventually see here pretty quickly how dy, the amount of vertical change in the tangent line, is going to approximate, again, delta y, which we're going to be identifying as the change in the tangent line, and delta y for the change in the actual function. As we get close to c, these values are going to be closer and closer together, and thus I have an approximation symbol between these. So tangent lines. We set these up using the point-slope form of a line that we learned again back in pre-algebra or algebra 1. So we have y minus y sub 1 equals m times x minus x sub 1. Using the point of tangency that we have in this diagram, we have y minus f of c equals f prime of c times x minus c. I've just basically, taken this x and y value from this point and come up with the equation of the tangent line, at least in general terms. Now I've moved this this negative f of c over to the right-hand side, and hopefully you might be able to, if you look at this long enough and you remember that the derivative is slope, we've got y equals slope m x, okay, and now this is x minus c, but it's some form of x, plus b. It's a form of the slope-intercept form you learned again way back in algebra 1. Now I'm not writing y equals mx plus b because if I had just a plus b at the end, that would be the y-intercept. That would be the value of the function when x is equal to 0. Well, our initial point, if you will, is, at least as far as this tangent line, is about that point of tangency. So our initial y value is basically like that f of c. So we got f prime of c, which now we know, of course we know first derivative is slope. So we have the slope of the tangent line, and we always say that slope is, change in y over change in x, or rise over run, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Well, sometimes it's more important to really understand or remember the real definition of slope, which is the change in y per 1 unit of change in x. So keep in mind on that. We have x minus c, which is going to be the change in x denoted by delta x. Oh, by the way, here, of course, if we take c plus delta x and we subtract c, we get delta x, that is that change in the x, plus f of c, or initial y value, where the tangent line is equal to the function value. Getting back to why I went ahead and just sort of called this point xy instead of using the initial coordinate of x plus, or c plus delta x. Well, if that's bothering you a little bit, let's take that x out. Let's replace it with that value of x we have here, and c plus delta x minus c comes out to be delta x. Now, if I take y equals mx plus b, and I take f of c and I subtract it kind of like back over to the other side like I had initially, I want you to see what's going on here. Y minus f of c is equal to f prime of c times delta x. Y minus the initial y value of f of c is that change in the tangent line, which you might just see someone just write these two equal to each other, not really understand where that came from. Well, it just came from the equation of the line. It's right there. F prime of c delta x is equal to y minus f of c. And keep it in this idea that slope is change in y per 1 unit of change in x. Well, slope is the change in the y value per 1 unit of change in x. So however much x is changed is how much the tangent line, moves up or down based on the slope. And that's where you get your vertical distance from. Okay, this is going to be our formula basically for estimating the change in y. Now, the math symbol for that, as we can see up here, this is going to be called dy, and I'm going to have this written in like a formal sort of theorem or postular, kind of like a statement here in the next screen when I erase all this graphs and symbols here. I'm going to formally just introduce that is labeled as dy. And the actual change in y, the actual change in the function, well, the function itself has the coordinate of c f of c, and, at least the way this is diagrammed, c plus delta x, f of c plus delta x. So, I'm just going to take that y value that's actually on the graph and subtract it with that y value, which is actually on the graph. And so we have f c plus delta x minus f of c, and that is going to be labeled as delta, did I say dx over there? I meant to say dy if I did not. And that's going to be delta y. So delta y is going to be the actual change in the function. Dy is going to be the estimated change in the function. It's going to be the vertical change in the tangent line. And again, if c is small, or excuse me, not c, but if the change of c, or delta x, or dx, I'm going to formally introduce that there in a second as well, how we're going to have dx in the label of delta x and dx and explain the difference. Actually, they're the same in a second. But as far as dy and delta x, again, estimated change in y, actual change in y. If delta x or dx is small, they're going to be approximately equal, and that's how your tangent line estimates your actual change in the function over a change in x. Let's get some more definitions down before we get to the examples and a couple of screens. Woo! Bang! This approximation, in this approximation, delta x is traditionally denoted by dx and is called the differential of x, and f prime of x dx is denoted by dy and is called the differential of y. Okay, let's look at the definition to help get this down before we start looking at some examples. The definition of derivatives is: let y equal f of x, let it represent a function that is differentiable on an open interval containing x. The differential of x is labeled as dx, and it's any non-real zero or any non-zero real number. The whole point of these differentials is to, and as far as we're going to look at it in this section, is to, allow the tangent line to estimate the change in y of the actual function, to help simplify some mathematics in certain situations and propagation of errors and such. So if there's no change in x between two x values, what amount of change in y is there to estimate? There is none, right? So the dx is just any non-real or non-zero real number. The differential of y, labeled as dy, is, before we finish this, remember, dy is going to estimate, or is going to be the change in y again for the tangent line, delta x, the change in y for the actual function, and if this delta x is small enough, your dy, your differential of y, is going to estimate delta y. Now, they're not the same thing. X and the change of x and dx, or delta x and dx are the same thing. Delta y and dy are not. So dy is equal to f prime of x dx, and it is the change in y within, that's how we want to think of it, or remember it, it's a change in y within a small neighborhood of, or near c. So we need to have relatively small delta x's to get a good approximation from our dy. If we take this, just to remember, just to have some kind of relationship with the previous math function that we've learned, if we take this dx and divide it to both sides, it's not really exactly correct, but it's a good technique of helping, allowing us to help remember this formula. Just kind of like this sort of also helps us to explain and remember the chain rule. If we divide both sides by dx, we can see the close relationship, at least as far as the notation is, to that of derivatives. We are going to, in a couple of scenes, see the rules for finding differentials, and they're going to look really the same as some of our basic rules for finding derivatives, like when you have a constant or the product rule or quotient rule or such. So if I take that dx and I subtract and I divide it over to the other side, we can see that we have dy over dx is equal to f prime of x. Really kind of very similar. Now, this derivative with respect to y is a math function. It's not really a ratio, but and there's certain instances where, or a lot of instances where, if we can kind of pretend that it's just a ratio, and the derivative of y with respect to x is not truly a ratio, but it can often be handled as such to allow us again to relate all these concepts we're learning and help us remember some of these formulas that we're learning through calculus. Okay, so we got some examples. We're going to start with tangent line approximation examples, and then ultimately do most of our examples with propagating error. Bam! First example. Find the tangent line approximation of y equals x squared minus 3x at the point 2, negative 2. Then use a table to compare the y values that you get from the actual function with, well, actually I said it backwards, with the linear function, your tangent line, with the actual function of, again, of course, that's y equals x squared minus 3x. Now all these values are pretty darn close to 2, which is going to be basically our point of tangency. So our value from our tangent line and the values from our function should be pretty darn close together. But we need a tangent line to finish the problem. So what do you need to write the equation of a line? Of course, you need a point and a slope. Now we have the point, which is 2, negative 2. What we need is slope. And of course, that means we need first derivative. So y prime, or f prime of x, is going to be equal to 2x minus 3. This, of course, derivative gives us the slope of this parabola at any point where the function is differentiable. Parabolas can be everywhere. But I really only care about the slope at that value of 2. So I'm going to do y prime of 2. And we get 2 times 2 minus 3, which of course is 4 minus 3, which is equal to 1. And that means our tangent line is y minus y sub 1 equals our slope, which is 1 at the point x equals 2, times x minus 2. And we have y plus 2 is equal to x minus 2. Go ahead and subtract both sides by 2, and y equals x minus 4. This is going to be our tangent line at 2. I think it's so cool that I'm going over a concept I teach in Algebra 1 and Calculus. I love how all this stuff just ties together. Okay, now I'm not going to break out a calculator and write all these values out for you, so I'm going to step off, reveal these answers. Again, I'm going to take these, what do we have here? 7x values, plug them into the function, see what those are, plug those same 7x values into our tangent line, and see how well this tangent line approximates the values at our function. Okay, so of course, again, as you saw from my diagram I finally erased, that the function and the tangent line are exactly the same at the point of tangency, and as you move away from the point of tangency, these values start to differ more and more from the actual function values to the tangent values, tangent line values. But you can see these differences are pretty small. Now, how close will they be? Well, that's going to be dependent, of course, on the curvature of the function as compared to the linear tangent line, and how far away you move from that tangent point. So, first example, tangent line approximations. Next! For our next example, sort of similar to the first one, I want to evaluate and compare delta y, actual change in y for the function, and dy, the estimated change in y, from the tangent line. So, even though we would kind of do this instinctively anyway, but to get this notation hammered down, delta y is the actual change in y. So delta y is going to be f of, well, in this case I gave you x, so f of x plus delta x minus f of x. I mean, we're finding the actual change in y, right? So we're just finding the two y values and subtract them. So our x value given is 2. So we're going to find f of 2, and we're going to subtract that with our x plus delta x. Well, our delta x is 0.1. Kind of like I said, we're getting to that estimating the propagation of errors. So that would be sort of like your manufacturing variability in a product maybe that you're making. So we have this dx, or delta x. So if our initial x value is 2, then we want to evaluate the function at 2 plus 0.1. Or, basically, just do f of 2.1 minus f of 2. Let's get that up there. So, whether that delta x is to the left or the right of 2, we have an actual change in the function of negative 2.522 units, or 2.282 units. Now, if we want to estimate that actual change in the function with the differential, then we need to remember that dy is equal to f prime of x dx. So we want to really just figure out what that derivative of find the derivative of our function, and our dx again is 0.1, and we're going to work that out and see how close the approximated value is to our actual change. So if y is 3 minus 2x cubed, then y prime, or f prime of x, is going to be just simply bring the 3 down. We got 2 times 3, which is negative 6x squared. And then our dx value, our amount of change, is 0.1. And that is going to come out to be dy. Okay, well, we need to bring our value of x in here, so we have negative 6 times our x value of 2 times 0.1, that's going to be negative 6 times 2 squared is 4. Can't believe I just paused on that. Times 0.1. That's 6 times negative 6 times 4 is negative 24. And negative 24 times 0.1 is negative 2.4. Now again, we don't know if this changes to, this delta x is just simply getting larger or smaller, so we'll come back here and say that our estimated change in y based on the tangent line from the x value of 2 is going to be plus or minus 2.4, and we can see that plus or minus 2.4 is a pretty close approximation of our actual change in the function. Our next screen is going to be dealing with calculating differentials and basically the rules you need to follow when writing those out, kind of like how I did here. Our differential of y is f prime of x dx. Well, there's some rules that will help us, do that a little bit easier. Or how about accurately? Let's go through working through the quotient rule here before I give you all the 4 basic differential rules. For example, u and v are differentiable functions of x. By definition, du, the differential of u, is equal to u prime dx, and the differential of v is equal to v prime dx. So we're going to go through this process and set it up. So we're going to take the differential of some function is equal to like f prime of x dx and see how that ties in with these definitions here. Well, the derivative with respect to x of this quotient is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. That is going to be over the denominator squared, of course. Now we're going to come in here and take this dx and distribute it through the parentheses, and we're going to get u, or v, excuse me, v u prime dx minus u v prime dx over v squared, and then like by definition in our example, the differential of u is equal to u prime dx. So u prime dx is going to come out, and we're going to have v du minus u, and v prime dx is dv, the differential of v, over v squared. So you can see this follows very closely with finding derivatives. So we're going to put the 4 rules of differentials over here, and I'm going to give you a couple of examples that I'm kind of going to pretty much allow you to do on your own and just show you the solution to make sure that you see the relationship between finding derivatives and differentials. So our 4 rules, basic rules for finding differentials, look very similar to the derivatives, right? The constant multiple, the differential of cu, a function with a constant multiple in front of it, is that constant. You can kind of pull it out front and take the differential of u. We have the sum and difference, the differential of the sum of 2 functions, u plus or minus v is the differential of u, plus or minus differential of v. The product rule, differential of 2 functions multiplied together is the first times the differential of the second, plus the second times the differential of the first. And the quotient rule, well, we just worked through that. Now, this is already a long video, the long introduction. I want to do a lot of examples about estimating propagated error and relative errors. So because of that, I'm going to step out. I'm going to show you 2 problems, examples of finding differentials, but again, they're so closely related to derivatives. I'm not going to explain them. I'm just going to bring them up here, let you pause the video, work them out if you like, and then reveal the solutions. We'll move on then to our first of the next example, again, starting to deal with, again, back toward tangent line approximations and estimating propagated error. This example is going to be similar to some of the earlier ones, but displayed graphically, and just in case that confuses you a little bit, here we go. Used differentials to approximate function values. F of x plus delta x is equal to approximated the original function plus the differential of y. Again, that's the tangent line approximation, which is equal to f of x plus f prime of x dx, because the directions say use differentials in the graph of the function f to approximate the value of the function at 3.05. All right, so we need to find f of, well, 3.32, that's the point of tangency here, is our original f, and I have a value of 3.05. So we're looking at a difference between 3.05 and 3, so it's f of x plus delta x, or f of 3 plus 0.05, is approximately equal to f of x, so it's going to be f of 3 plus the differential of y, but that is equal to f prime of x dx. Okay, so f of 3 is equal to 2, that was pretty simple, plus f prime of x, that's going to be the slope of the function at x. Well, we have, conveniently, a tangent line, thus we have a slope of the function at 3, 2, and it looks like that from conveniently placed, we have a y-intercept of 3. So if I go down 1 and over 3, that's the slope of the tangent line, or the slope of the function at the point 3, 2. So f prime of x is equal to negative 1/3. And then dx, we're moving to the right. Again, dx is equal to, really I found it here, dx is the difference between our two values. And 3.05 minus 3 is, a difference of 0.05. So we have 2 plus negative 1/3 times 0.05, and that comes out to be approximately equal to 1.983, which would make sense that the function value just a little bit to the right of 3.05 would be a little bit less than 2, because the function, had a negative slope there, and it's going to continue to be negative for a while until maybe there's a relative min here and it starts to right up again, but that seems like a reasonable value. Now, I followed the directions to a T, saying that I'm using the differentials, but it is called, a tangent line approximation of the function. So there's another look to this solution, which I'll give us right now. It's actually a little bit less notation, but this is good for remembering what all those notations mean. Now, if you remember that this process is called tangent line approximation, all that nice notation and remembering that or delta x and dy and dx and all that good stuff, what all that means and represents in the function, which is key for this section because we're just introducing it. But if you remember it's called tangent line approximation, you can just find the equation of the tangent line, which is going to be y minus y sub 1 equals the slope, and the slope at that tangent point of tangency was negative 1/3 that we used to make the tangent line, times x minus the x of the coordinate, which of course is 3. We take this negative 1/3 and distribute it. We get y minus 2 is equal to negative 1/3 x plus 1. Take the 2 and add it over and get y is equal to negative 1/3 x plus 2. And now if we take that function, or that value of that function, that 3.05, and plug it into our tangent line, y of 3.05 is equal to negative 1/3 x times 3.05 plus 2, and guess what that comes out to be? 1.9833 again. So that is again our approximated value based on the tangent line of the actual function. Won't be exact, but it's a very close approximation as we're learning. Okay, now we're going to go through 3 examples of estimated propagated error. Word problems. Woo! Everybody's favorite. Now with measurements, we're never going to be exact, and when producing products, manufacturing, everyone's not going to be exactly the same. There's always going to be a little bit of error. So we take a measured value, but then there's going to be some kind of error, as much as we try not to, between a measured value and an exact value answer. And the difference between the exact value and the measured value is going to be delta y, which we're going to estimate with a differential of y. And when we're asked for relative error, that is a percent, simply. So part over whole. How much error is there over the original measurement? Okay, so our example here is you measure the base and height of a triangle to be 20 inches and 16 inches respectively. So the base is 20 inches long and the height is 16. So I'm going to go ahead and stop there and write that down. So our base is 20 inches. The height is 16. Okay, I'm sure we're going to need that information. There is a possible error of 1/3 of an inch, but I think I actually meant for that to be 1/8. Yes, I did. So 1/8 of an inch. So we have the measured difference either way, whether it's dB or the differential of B or the difference in H is going to be 1/8 of an inch. All right. Use differentials to approximate the possible propagated error in the area. So differentials. So we're looking for dy is going to be equal to f prime of x dx, at least in terms of the general definition. So we want to find the propagated error in the area. So we want to find dA. Okay, well, we're talking about a triangle. So the area of a triangle, that function, is equal to 1/2 base times height. So we're going to need to find the differential using with the product rule. So we have dA is going to be equal to 1/2 b dH okay, like basically like, you know, first times the differential of the second plus the second times the differential of first. And I could have left the 1/2 out front. Maybe some of you prefer that that you would do that. So we have H times dB, or 1/2, the differential of B, or just dB. Okay, or you can have the 1/2 out front. I'm actually, now that I've written it, thinking maybe that would have been cleaner, but let's just stick with that. So we have 1/2, the length of the base, which we got was 20. The differential, or the possible error in the measurement for dH is 1/8, plus our measured height is 16, times 1/2. Again, dB is equal to, or given to us, excuse me, as a value of 1/8. And we have 2 times 18, which is 16, so we have 20 over 16, plus we have half of, well, 2 times 8 is 16, and 16 over 16 is 1. And that comes out to be, well, let's see here. This is going to be 20 over 16 plus 16 over 16, and that's going to be 36 over 16. And that means that dA, 16 times 16 is 32, so 2. And I said 32, right? And that leaves me with a remainder of 4, and 4 over 16 comes out to be 1/4. Now this is the propagated error, the estimated approximating the possible propagated error in area. So our unit of measure here is 2 1/4 square inches. There's A. Now B says to find approximate the percent of error in the area, or find the relative error in our possible propagated error in the area. So that means that we want to find, oh, excuse me, by the way, it's not necessarily that the object, that the measurements are too small and they're all going to be larger. So this is our estimated, or my approximation of the possible propagated error, but my measurement could be too large or too small. So I almost forgot to come back here and say that actually dA is really plus or minus. You know, we can be off a little below or a little above that 2 1/4 square inches. Now our relative error, or percent, again always being part over whole, is dA over A. And that means that we have 2 1/4, or putting this in a proper fraction form, 9 over 4, over the original area that we measured of this triangle. And that's going to be 1/2 times the base, which is 20, times the height of 16. And when we get done cleaning that up, just to speed this up just a little bit, we come out to be to a value, approximated value of 0.014. So our area has a relative error of approximately, again, because that's what we're doing, approximately 1.4%. Now, you can again do this as a plus or minus, because we can be, our measured error can be above or below. The solution book, my solutions guide, when they go ahead and find the percent, wraps this in a set of parentheses to give just that positive answer. But again, your measurement can be, a little bit above or below the actual area, and that would give you an approximated relative error or percentage of error of 1.4%. And that is the end of our first example. The measure of the circumference of a circle is found to be 48 centimeters, with a possible error of 0.8. So they gave us circumference, so they gave us C, which is equal to 48, and we know the circumference is equal to 2 pi r as a formula, okay? And they gave us a possible error of 0.8. Now, is that a possible error? What were they measuring? Were they measuring the radius? Did they give us dr? Or were they measuring the circumference, and thus they gave us dc? Well, we're talking about measuring the circumference, the distance around. So dc is equal to the 0.8. Okay, well, let's get to the question. Approximate the percent of error, just to make the question a little bit more difficult for our examples, in computing the area. It's like the other ones, previous one with the triangle. We're going to find the differential in the area, the approximate propagated error in that measurement of area, that calculation of area, but we're going to find the percent. So we're asked to find, really what we're asked to find is dA over A, but we're not going to be able to find that unless we first find dA. So this is what our final answer is going to be, but right now we need to start off by figuring just what is the approximated propagated error in the area. Well, area is equal to pi r squared. So we're going to be looking for dA, which is going to be A prime over, and looking at this formula, it's going to be A prime dr. Okay, well, A prime is 2 pi r dr. All right, so we're looking for dA, and the radius. We don't have that. dr. Yeah, we don't have that either. So we're going to have to stop our problem, really, and go back to the information and pull out the information that we need. Like, well, what is the radius? Well, we have right here a formula for the circumference, which is 48 equals 2 pi r. We can divide both sides by 2 pi and get that the radius is equal to, actually, it's not a good idea to just keep swapping things back around for, so I'll keep r on the right. So we have r is equal to 48 divided by 2, which is 24 pi. Okay, great. So I can come in here and get 2 pi times 24 over pi, but I still don't know my differential in the radius, my measurement error in the error in the radius. So, well, what's that? Well, it means I need to come back up to here and go, okay, well, I have C is equal to dC is equal to C prime, and since this formula is got an independent variable of r, it's going to be dC equals C prime dr. Well, dC, we're given that. It's 0.8 equals C prime, the formula for circumference, the derivative of that. Well, the derivative of 2 pi r is going to be 2 pi, and all left is dr. Now, we already have decimals in here, and, well, 8.8 is 8 tenths, and we can take 8 divided by 10 and multiply both sides by 1 over 2 pi, but we're going to need a decimal approximation for this anyway, because my students are going to be allowed to use calculators on these problems. So 0.8 divided by 2 pi is going to be approximately, because we're now rounding off some decimals, it's going to be approximately 0.12 0.73, and this is in centimeters. So we're talking about, yeah, the DR value for our radius is going to be 0.1273 centimeters. Now I can come back up here and plug that in. So DR is 0.1273, which means that my differential of A, or my estimated error, propagated error in the area, is going to be equal to approximately plus or minus 6.11 centimeters propagated error in area, so centimeters squared. Excellent. Okay, let's get the second part of this question up, as well as the percentage. That's going to be the absolute value of 6.11 divided by the, I guess I could write that up here. I'm going to have to erase this work here in a second. But the relative error is going to be the absolute value of dA over A. That's going to be approximately equal to 6.11 divided by the original area. Well, area is pi r squared, so it's going to be pi times the radius, which we have labeled as 24 over pi, still in exact form. The pi's will cancel out, and 6.11 divided by radius squared. So that means I need to kind of pause and clean this up a little bit. All right, that's better. Part over whole comes out to be approximately 3.33% as our approximated relative error in the area of that circle. Now I have a part B to this question. We're going to kind of work it backwards, give you some restrictions on the amount of error we can have in the area, and translate it backwards into some kind of information about the circumference. For our second part, estimate the maximum allowed percent in error in measuring the circumference if the error in computing the area cannot exceed 2%. So the computing the area cannot exceed 2%. So dA over A must be less than or equal to 0.02, and we're just going to work this backwards and get into circumference, just like we had to go from circumference into area for part A. So it's kind of like just a reverse problem. So area is pi r squared. So dA is equal to pi r squared, and that means again to be less than or equal to 0.02. Then we're going to bring this over to the other side, and dA is equal to 0.02 times pi. Now our radius, remember we had, was 24 over pi squared, and right off the top of my head, 0.02 times pi times 24 squared comes out to be approximately, less than or equal to, a decimal version of that is 3.667 square centimeters. Okay, now we got dA. All right, well, what does that mean? Well, dA, the formula for that is equal to the differential of A, or area, is equal to A prime, and area is, again, pi r squared. The independent variable is r, so it's going to be dr. And dA, we know now, is going to be, needs to be less than or equal to 3.667 square centimeters. So this is going to go in its place, and A prime dr needs to remain less than or equal to 3.667, and area is pi r squared, so A prime pi r squared is going to be 2 pi r. Okay, now let's get that radius back in there and figure out what is our allowable measured error, or allowable error in the measurement of the radius. Okay, so there we go. Based on that parameter again, that our percentage of error on the area, or relative error, cannot exceed 2%, we get that the dr value, the largest possible amount of error that we can have in the measured radius, is got to be less than or equal to plus or minus 0.0764 centimeters. Okay, now getting back to the question, of what estimate the maximum allowed percent of error in measuring the circumference means that we need to find this is going to be dc over c. So dc is going to be equal to c prime dr, and so dc circumference again is 2 pi r. The derivative of 2 pi r is 2 pi, and then dr. All right, so we got dc is 2 pi. Our dr value again is approximately 0.0764, and that right off the top of my head comes out to be that estimate the maximum, I keep forgetting the inequalities, the maximum allowed error. So this has to remain less than or equal to, 2 pi times 0.0764 comes out to be plus or minus 0.47979 centimeters is our largest allowed estimated error in the measurement of the circumference. So then the percent is going to be dc over c, which is going to be and go ahead and let's just wrap an absolute value around that so we have just a positive percent. Or you could say maybe your teacher, just match whatever your teacher wants. Do they want a positive answer, or do they want like a, you can be off by plus or minus this percent? That's going to be 0.47979 over the circumference, which is 2 pi. Again, that radius is 24 over pi, and that as a decimal answer comes out to be, one more time, the maximum allowed percent of error in the measured circumference comes out to be, approximately equal to 0.01 or 1%. Now, this is kind of just working through it all of it with arithmetic and maybe the use of our graphing or our calculators. If you want to sort of put this calculation, keep it in terms of the formulas until the very, very end and maybe get a more exact answer, or maybe you're doing this work and you're not allowed to have a graphing calculator to help you with the work. Well, then this part here of all of this actually together can look something like this. My solutions guide in my book just has this sort of pop up and just boom, there's the answer, without showing how all of this can work. But I can put these together again without crunching the numbers all the way through as we go. I'll just reveal that to you. Now, if you're getting real fancy with your algebra and you're not using your calculator, we have, again, dA over A had to be less than or equal to 0.02. Well, the differential of A is A prime dr, and the area formula is pi r squared. Bringing in the idea that you have to bring circumference in as opposed to area, and you have this dr here, well, dc, the differential of the circumference, the area and the measure of the circumference, is equal to c prime dr. And we can solve that for dr, and that allows us to take dr out and replace it with dc over c prime, bringing some circumference measurements in here and getting the area measurements out. Okay, well, a prime, again, area is 2 pi r squared, and the derivative of that is 2 pi r. That's going to allow some cancellation here. And what do we have? Well, the cancellation allows us to have r over 1 in the denominator after the pi and one of the two r's cancel out. I went ahead and brought this denominator of r over 1 and flipped it up and changed it to multiplication. We got 2dc over c prime of r. Okay, well, c prime, circumference is 2 pi r, so the derivative of that is 2 pi, so c prime comes out, 2 pi goes in its place. The 2's cancel out, the radius is 24 over pi. Okay, well now the pi's are canceling out. We got multiplying both sides by 24, and we have dc, the approximated propagated error in the circumference, or our largest allowable error in the measure of the circumference, is 0.48. So now dc over c is 0.48 over c, which is 2 pi r. A lot more cancellations happen. We get 0.48 divided by 48, and voila, the answer is 0.01 or 1%. Hope that makes sense. I'm just sort of pausing and laughing in my head because as I work these problems and of course pre-work this homework before my students do it, and I check my solutions as I go, because even I need to check my own work. All of this algebra is basically written in one line in the solution guide, much less the solutions in the back of the book. So that's how you can do this without just calculating all the small arithmetic steps along the way. One more example. The measure of the leg of a right triangle is found to be 7.2 centimeters, and the opposite angle is 31 degrees 35 minutes, with a possible error of 20 minutes. Approximate the relative error, again percent, in computing the length of the hypotenuse. In other words, we're looking for dh over h. So we're going to have to find h, the measured length of the hypotenuse that we actually have from the numbers given, and dh, the error, the estimation of the error in our measure of the hypotenuse, because we know we have some error in that measure of the angle. Okay, well, if you'd like to turn your minutes into a decimal form to make it a little bit easier with your calculator, then you're going to want to divide those by 60. So this is going to be equal to 31 degrees and 35 over 60. We'll come up with a decimal of that in a second. And this is going to be 20 minutes over 60 to turn that into 60 minutes to turn that into a decimal. So these are going to come out to be, right off the top of my head, voila, 31.5 833 degrees approximately. So let's lose that. And our d theta value is equal to approximately 0.33, well, carry out as many threes as you like, degrees. Now, if you work out this problem in terms of degrees, your estimation of the propagated error in the hypotenuse is going to be like almost the entire length of the hypotenuse. We need to convert these degrees into radians. Now radians, remember, radians is a ratio basically of the circumference and the diameter, or it's the number of radiuses it takes in a circle to get, say, halfway around that circle. So there is some kind of idea of length built into the rotational measurement that's radians, another way of measuring rotation. So because of that, we need to get these degree measures converted into radians. So we're going to multiply each of these by pi over 180. And again, these values in measurements of radians is going to be approximately equal to 0.5512 radians, and approximately for our d theta value of 0.0058 radians. Now, okay, so now we have our measurements and something that will actually give us a good answer when we're done. All right. Okay, so we have our angles in terms of radians. Now, looking at the triangle, what trig function is going to relate all this information together? Angle, opposite side, hypotenuse, opposite side, hypotenuse. Yeah, that's sine. So we have the sine of theta is equal to our opposite side of A over H. We're going to be ultimately looking for DH. Let's get this equation solved for H. That's going to be multiply both sides by H, and we get H sine theta equals A. Divide both sides by sine theta, and we get H is equal to A over the sine theta. Now for DH, remember that's going to be H prime, and this is in terms of theta, so it's going to be H prime d theta. So we're going to, for purposes of finding H prime, write this as A sine to the -1 theta, just getting that sine function out of the denominator. Actually, that kind of looks like an inverse function, so let's do that instead. Now H prime is going to be equal to, bring that -1 down, we have negative A sine theta to the now -2 power, and we're doing the chain rule. So now we brought that -1 down, we reduced the exponent by 1, now we need to find the derivative of the inside function, and the derivative of sine theta is cosine theta. And I think I'll have to erase some of the scratch work as we go. So this cleans up to h prime is equal to negative a cosine theta over sine squared theta. So now dh is equal to negative a. I'm gonna leave it like that. We have negative a cosine theta over sine squared theta d theta. Now we have the differential equation. Now dh is equal to negative a. Well, our a was measured out to be 7.2 times the cosine of our theta value, which was 0.5512, over the sine squared theta. So again, that's going to be the sine of 0.5512 squared. And d theta, or possible error in the measure of the angle, was 0.0058 radians. That comes out to be a DH value that is equal to, let's just make sure I didn't write anything wrong up here. Nope, that comes out to DH, or estimated propagated error in the measure of the hypotenuse, comes out to be approximately, really kind of, this should be as well because of our rounded off decimal values, of plus minus 0.1297. We're measuring hypotenuse and length, so that'll be centimeters. Now, I'm kind of out of room, so let me pause the video, erase this stuff, and we're going to set up to find our relative error, or the percent of error, and the length of the hypotenuse. We got that DH value, our relative error. Again, DH over H, you could do plus or minus, you could do absolute value, just get a positive percent. Comes out to be 0.1297 divided by our actual height, which is A, which was 7.2, divided by the sine of theta, which was 0.5512 radians. And that comes out to an approximate value of 0.00943, which means your relative error is approximately, for the measurement of your hypotenuse, 0.943%. I can't believe I just looked at my notes to write a decimal as a percent. I must be tired. Long video. Thank you for watching. Hopefully with my all my vocabulary and math symbols and examples, I've given you enough to go do your homework.